Testing, 1, 2, 3, testing, 1, 2, 3. All right, I'll start talking about these videos for our audience here and anybody who's interested. So, these videos show perception functionality in a variety of urban and highway use cases for self-driving cars and robotics. Oh yes, welcome. Please have a seat, anybody who wants to have a seat. As a bit of background, Helm.AI builds scalable AI software for self-driving cars and robotics. And our key technological differentiator is an approach we call deep teaching, which uses unsupervised learning to make this process more robust and scalable. What do I mean by scalable? Well, basically, in the standard machine learning approach to developing these models, you have a heavy reliance on human-labeled data. In the standard approach, every time you encounter some new situation or task, you need to get humans to label all kinds of images for you to be able to make that functionality. But really, I mean, this can get way too expensive because there's just a huge amount of things and a huge amount of situations that can happen in reality. It gets exponentially expensive. So Helm's core approach is to use unsupervised learning to make this more scalable. All right, so in these various videos, we're showing off what this technology can do in all kinds of interesting and challenging situations. This video shows sensor fusion between LiDAR on the left and vision on the right. So Helm's technology is based only on vision, only on understanding images. This is we believe this is a key thing because yes, LiDAR can help you kind of get some information, but LiDAR isn't always going to be available if there's like heavy rain or dust and it's not available in the distance. But okay, moving on to this video. This video and the next video are kind of a bit different, kind of a bit unorthodox. This is some drone footage from the web, and it's very different from what you would encounter in a typical self-driving use case. But our technology generalizes very well, performs very well in that new situation. Likewise, here's another new situation. This is some mining scene. And this is kind of a use case I'm personally very excited about. I feel like when we talk about autonomous vehicles, we often just talk about the consumer use case of like robo-taxis and, I want my car to drive me to work. But when you think about mining and industrial applications, there's a lot of value being added to the world in these big mines and stuff. But these are very difficult tasks. They're dangerous for people to do, and they're out in the middle of nowhere. Adding autonomy here is something that could be very useful. And so Helm is very excited to be working on this. And again, a key thing to note here is that this is very different from the typical consumer driving use case, which is shown here. But our technology generalizes well to that new situation. But okay, returning to our bread and butter product, this is our L2 highway autopilot system. This is what OEMs, car manufacturers, want to start with when they start working with us. Because this is kind of like the base layer, most fundamental type of autonomy you might want to have in your car. So this is one of our cars. This is my friend and employee, Sung. He is the main guy for the fleets. And the car is driving itself on the highway here. And basically, in order to drive reliably on the highway, you need a small set of predictions done very reliably and kind of robustly. And they're shown in the left over here. So okay, what are these predictions? Well, okay, at the base layer, you need to know where the road is, where free space is, and you can drive. That's shown in blue. You need to know the lanes, so you can keep the lanes. And you need to know the locations of the other vehicles. And if you can see on the bird's eye view, the video has changed, but the bird's eye view there was constructed just from detection on the image. That's a key thing to emphasize. There's no LiDAR going on here. No LiDAR, no radar. Just doing predictions of depth and orientation from the image, like people do. Now, okay, moving on to a more complicated situation. We were just looking at the highway system, right? Now, moving into urban situations and these kind of, again, more complex situations, you need more granular information about these various objects in the world around you. So for example, here we have lane classification shown, and again, it's switched, but classification between white lanes, yellow lanes, and other, which is relevant because, a white lane means that cars are going the same direction, yellow means different directions. Likewise, in urban environments, there's all kinds of rich road marking information. Like you can see the crosswalks are shown in teal, and there's very semantic information in yellow, like ride share, stop, and so on. That all needs to be parsed out of the image in a reliable way and handed up to the planning and control part of the system. And again, as a basic kind of background, every autonomous system has the following core structure. There's the vision system, which tells you what you're looking at and what's around you. And then there's the planning and control system that takes those detections and figures out how to navigate through the world using them. So OEMs, car manufacturers, ideally, I mean, they have teams working on all that stuff, but the vision problem is incredibly hard because there's this huge, like, long tail of potential new objects and new situations. It's actually, I mean, remarkable when you think about us people. Like, when a child learns kind of the basic idea of what a car is, that generalizes to all kinds of new cars that it sees. That's kind of, I guess, related to what we call common sense. But you know, common sense is actually a very special thing and something that's very hard to create in machines. Because again, the standard machine learning kind of engine or crank for developing this software, it relies heavily on this supervised learning based approach that gets just exponentially expensive if you're only using that. It gets exponentially expensive to need to get human labels for every new situation and task that you want to perform on. So the key kind of technological innovation or technological edge behind Helm is we're using unsupervised learning to make that way more scalable and way more doable without the exponential increase in cost. And the basic idea here is like, using unsupervised learning, you can make this base layer model about physical priors of the world, like, you know, the nature of what is a road and what is an object and what are kind of what's the vague idea of these things around me. And then once you have that, it's way easier to adapt to these new situations and these new tasks. And this is kind of on display here in this final set of videos. This final set of videos is really my favorite set in this overall video that shows the full set of functionality you need to drive safely in an urban environment. So it's like a superset of the stuff we were looking at in the highway situation. There's like free space in blue and the lane markings and the road markings. And on top, you've got the cars, bicycles, motorcycles, and people. All of this is kind of coming together into our urban autopilot system, which again is like the next step that OEMs want to work with us for. So okay, that concludes the video. Maybe I want to just pause and say, well, first I want to say thanks everybody for listening. And if you have any questions, I'm happy to talk with you more, but also just feel free to hang out, feel free to take some materials, take some snacks. Yeah, thank you very much. Thank you.